Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder if the way we measure things like intelligence or personality is actually giving us the full picture? Today we're diving into a fascinating study that asks a super important question. When psychometric models treat things like abilities or attitudes as being on a number line, like a ruler, are they really measuring them that way? Researchers often assume that psychological traits are interval level. Meaning not only can we tell if someone has more or less of a trait, but also that the difference between a score of 10 and 20 is the same as the difference between 70 and 80. But is this assumption always true? And more importantly, can we even test it? Most of the time, when psychologists create tests for things we can't directly see like intelligence or personality, they assume these hidden traits are measured on a scale, like temperature or height. Think of things like factor analysis or item response theory models. They estimate where someone falls on this continuous scale, and these models work well. But the researchers in this study point out something crucial. Fitting these models doesn't automatically mean the trait is interval scaled. It just means the model works with that assumption. So, the big idea here is to create a way to test this assumption. Instead of just assuming interval level measurement, they want to see if the data really supports it. They propose comparing different types of models. Think of it like this. Model 1 is the weakest. It just says things can be ordered, like ranking people from best to worst. Model 2 is a bit stronger. It assumes an additive structure, meaning the parts add up in a meaningful way, which is closer to interval level, but without a specific mathematical shape. And Model 3 is the strongest, like the well-known Rasch model, which assumes both additivity and a specific mathematical curve for how responses relate to the trait. This idea of what makes something a true measurement has been debated for a long time. Some say the math of the model proves it, while others argue you need solid evidence that the real-world relationships match the mathematical ones you are using. This study leans towards the latter, using something called representational measurement theory, which is all about whether the numbers we use actually reflect the real-world relationships we care about. So they're not just asking if a test gives you a score, they're asking if that score is like a ruler. With a ruler, if you move 2 inches, it means the same thing no matter where you are on the ruler. An ordinal scale, like a ranking, only tells you who is higher or lower. An interval scale tells you how much higher or lower, and those how much amounts are consistent. The key here is that by comparing these models with different levels of restrictions, they can see which one best fits the data. If the simplest ordinal model fits just as well as the more complex interval models, maybe we don't have enough evidence for interval level measurement. Before we get to their approach, they briefly touch on other ways people try to figure out measurement. There is something called taxometric analysis, which tries to tell if a trait is more like a category or a continuous thing. But the researchers say that is different from the ordinal versus interval question. Also, they discuss the Rasch model, which is often seen as a good measure, but they argue that even if the Rasch model fits the data well, it doesn't prove interval measurement. It might just be that the Rasch model's assumptions are flexible enough to cover other scenarios too. This is where their specific models come in. They use 3 ISOP, which is for ordinal data, meaning it only cares about the order. Addisop, which adds the additive structure, but doesn't assume a specific math function for the response probability. And the Rasch model, which is additive and has a logistic function. This creates a neat hierarchy to test. To test their idea, they did a big simulation study. They created a bunch of fake data that they knew was generated with an additive interval-like structure, specifically from a Rasch model. This is like creating a perfect scenario to see if their methods can pick up on that structure. They varied things like how many items were on the test, how many people took it, and how many answer choices there were. They ran 4,500 different scenarios. Then, for each scenario, they tried to fit these 3 models, ISOP, Addisop, and Rasch. To decide which model was best, they used something called information criteria. Think of these as smart ways to balance how well a model fits the data with how complex it is. More complex models can sometimes fit almost anything, so these criteria penalize them. A big challenge was that the ISOP and Addisop models are a bit trickier to count the complexity of, so they used a clever method called bootstrap, estimated effective degrees of freedom to get a consistent measure for all models. The results were really interesting. First, they found that different information criteria often pointed to different models. This is shown in Figure 2. AIC, Beak, and HQC generally showed similar patterns, but the bootstrap dig acted differently. This tells us that just relying on one number isn't enough. You need to look at how different methods agree or disagree. For example, with the AIC criterion, when the tests had more answer choices, polytomous data, like multiple choice with 5 or 7 options, AIC often preferred the Additive model. This is great because it means AIC found evidence for the additive structure, but didn't jump to the strong assumption of the Rasch model's specific curve. However, for simple yes-no answers, dichotomous data, as the test got longer, AIC started to favor the simpler ISO model, the Ordinal one. This is a bit surprising because the data was generated from a Rasch model, which is additive. It suggests that with more items, even AIC struggled to see the additive structure. Beak was a bit different. It tended to pick the Rasch model more often for shorter tests with simple answers, especially with more people. But like AIC, it also shifted towards ISOP for very long tests with simple answers. For tests with more answer choices, Additive was often favored. The Hannon-Quinn criterion was somewhere in between. It also showed that more answer choices often led to Additive being preferred, suggesting the additive structure was identified. But for simple dichotomous questions, the results depended heavily on the number of items and people, with longer tests sometimes pushing towards the simpler ISOP model. The bootstrap dike showed a really different pattern. For simple dichotomous data, it strongly favored the Rasch model as the tests got longer. But for tests with more answer choices, it often picked the Ordinal ISOP model for shorter tests and then shifted to Rasch as tests got longer. And importantly, the dig had a big problem. It couldn't even be computed in many of the scenarios, especially with few people and simple dichotomous questions. This makes it a less reliable tool. Then, they applied this to real data from the Brazilian National High School Examination, or NM. This is a big test with multiple choice questions. They looked at data from about 500 students and then from over 4,600 students. With a smaller sample of 500 students, the results were all over the place. Some criteria, like the simple ordinal model, is up, while others liked the full Rasch model. At this up, the middle ground wasn't favored by anyone. This shows that with less data, it is hard to get a clear answer about the measurement level. When they used a much larger sample, AIC, Beak, and HQC all agreed on the simplest ordinal model is up. The dig still liked the Rasch model. This might tempt you to say NM isn't interval, scaled. But the researchers caution us. They remind us that their simulation showed that with long, simple tests, these criteria can favor ISOP even when the data was generated from a Rasch interval. Like models, so even with a lot of data, it doesn't automatically prove the absence of an additive structure. So what is the big takeaway? The researchers successfully created a framework to empirically test the assumption of interval level measurement. By comparing models with different levels of complexity, they can see if the data truly supports an additive structure or just an ordering. The most important finding from the simulation is that there is no simple rule. What works best depends on many things combined: how many items you have, how many people are taking the test, and how many answer choices there are. This means the evidence for interval measurement is often conditional. This is crucial. No single statistical criterion is perfect. Agreement across multiple criteria gives you stronger confidence. Disagreement suggests the data might not clearly support one measurement level over another with the current approach. The NM example highlights this. With a lot of data, 3 criteria pointed to a simpler ordinal model, while one still favored the more complex Rasch model. This disagreement shows the uncertainty. It doesn't definitively prove that the NM scale isn't interval level, but it shows that the conclusion depends heavily on which statistical tool you use, and that more research is needed to calibrate these tools for specific situations. This research is a big step because it makes the assumption of interval-level measurement testable. Instead of just assuming it, you can put it to the evidence. It complements other methods that directly check mathematical rules, offering a more comprehensive model comparison approach. Now, like any good science, there are limitations. The biggest one is that their main simulation only generated data from a Rasch structure. To really test the method, they need to see how it works when data is generated from genuinely non-additive or additive but non-logistic models. They also want to explore different ways of scoring multiple choice answers and different ways of estimating model complexity. And the dig, as we saw, had problems. But even with these limitations, this is a really exciting development. For too long, Psychometrics has often just picked the most complex model that fits, implicitly assuming interval measurement. This new approach flips that it puts the level of measurement itself up for debate. It is asking, do we have evidence for just an order or for additivity? Or for the full specific Rasch model, making these assumptions testable is a huge step towards more robust psychological measurement. It's like moving from just guessing if a tool works to actually testing its precision and what it's truly capable of measuring.